All right, so we immediately transition to our Jupyter Notebook walkthrough, right? Again, just to mention that this companion Jupyter Notebook, so the PDF itself, the transformed PDF, and the actual IPython notebook file will be made available via Google Classroom, right? So that you can go through it at your own time. And again, I do highly recommend that you at the very least, just try and understand what's in here, because again, we're going to be building up from we're actually going to build up from this particular notebook when we start looking at the different estimators that we get to work with, right? So you want to probably do that. All right, so what I'm going to do is I'm just going to, let me see here, I'm just going to, this is clear enough, it should be, looks visible enough to me. I'm going to clear the output, and then we'll start rerunning this from scratch, right? Simple walkthrough here. Again, the preamble can be ignored. It's just there to help us generate the header here for the PDF document and the table of content, or the table of contents rather. So what we're essentially just going to go through here is a few examples on how we get to transform the two different types of categorical attributes, so nominal attributes and ordinal attributes, and then we'll look at the bag of words model, and I can just do that, term frequency. Term frequency model, and then TF-IDF. All right. Oh, and then there's a note here. Again, this is linked to what I said earlier, where I was saying that you probably want to download the most recent versions of the notebooks. What you immediately notice from the data frame is that the merged data frame actually does have a few derived attributes. These are linked to the exercise that you were meant to work towards, and we forgot to find out if people actually did manage to work towards the exercise. So you probably want to take note here. And again, as a reminder, again, we are still working on, we are on phase number 3 of the CRISP DM model, essentially data preparation. So we're looking at data transformation. These configuration details are just there to help with the output cells within pandas, so that we get a more visually appealing output in these cells, right? It's mostly associated with these tables. That's why I have little code there. And then, as always, we have a section that has import statements associated with the different packages that we're making use of in this particular notebook, right? And you notice that the very first thing we are doing here is we are loading the saved pipeline from the previous stage of our pipeline. So previously we went through a systematic process of deriving attributes, and I guess we should have appropriately named these based on the different phases, but that's fine. So you will notice that this Pico file that we are loading is the one that was, where are you, data preparation, the one that was the one that was saved as part of this part of the pipeline. So it was done here, right? And we're using joblib essentially to just save the state or serialize it to disk. Okay, so we load it. After we load it, for good measure, what we're doing in this cell is we're just confirming that what we've loaded is actually what we want to work with. And the way that I normally do this is I just check the columns. I then I count the number of observations I have in that particular saved state that I'm working with. In this case, you notice that I have 23 observations, and I can really easily confirm that what I'm doing is actually correct here by going to the previous state. And I guess I'll have to rerun this thing here, but anyways, I count the number of observations. So the number of records that I have in here is 123. It should be able to color rate should be exactly the same as the number of observations that I have here. If only we can find a cell that already has this run. There we go, 123, right? Okay, next thing we do is I hate it when this happens. The numbering of the cells, I'll have to clear this and restart, right? If you notice, I ran the cell multiple times, and so the numbering of the cells is a bit distorted. Not that it matters, but I don't know why I did that. That's stupid, but okay. So we load the saved state. We verify what we've loaded to confirm that it's actually what we want to work with. And then again, the other way of verifying is you just take a peek at the observations to confirm that the data that you have is what you want to work with, essentially. So we are using the head function to just view the first 3 observations, right? So this is essentially the structure of our observations, 153 columns. You notice the number of columns have changed when compared to the previous saved state. We previously had, I think, 151, if I'm not mistaken. We have 153 because we have 2 additional derived attributes. Specifically, what you will notice is we have derived the age. Yeah? We have, and you probably want to look at the revised notebook associated with data preparation to see how we computed the age. But there's nothing new there. What we're doing is just subtracting the date of birth from the year when this particular student, in this case, was taking or enrolled into this course, right? And so we come up with, oh my goodness, where is that thing? Where's age here? Can't see it. I guess it's hidden somewhere. Shoot. Okay, but essentially what we're doing is we're subtracting this academic year is the year when the student was in first year or enrolled into this course. And then we subtract the date of birth, which is here. So we subtract 1999 from 2019 here to get the I wish we could see where's the date of, where's the age here? Ah, there we go, to get the student age here. So this particular student is 20 years old. This one is 19 years old. This observation has now entries for these other attribute values here, because this was just a test. This was me actually, by the way, right? This is why you have data mining, which is an outlier here. Okay, so we've confirmed that indeed this is the data frame that we want to work with. The next thing we do is in this case, we are creating a new data frame. Now, you notice that in this particular stage, what we're doing is we're creating a data frame by filtering out entries where a student did not write an exam, right? It's just it's a choice, it's a decision we've had to make, because one of the things we want to do is we want to identify if there's a correlation between, or a causal effect between the different attributes, input features, in relation to the output, which is the exam, right? So because our exam is a dependent variable, we want to make sure that it has values associated with it, which is why in line number 5, you notice that the filter for the data frame we've just loaded says only pick records where the exam score is not now. So the student wrote the exam. Again, for good measure, we just inspect the newly filtered data frame. And again, what we could have done here is we just said count the number of the observations, because previously we have 63 now. Previously we had 123. We now have 63. It's a bit weird, I think, but something to look at later, I guess. I don't know. Something iffy here. I'd have to verify but it's fine. We'll have to just verify the data sources that we're actually working with the correct things, because it appears we have, if you notice here, if we subtract 123 from 69, 123, oh Jesus, decimal, 123 minus 63, we have 60 observations that we are omitting here. I wonder why. I guess it's probably something to do with the joins, but that's fine. It won't prevent us or deter us from proceeding further. Doesn't change a thing. All right, so again, in terms of the attribute selection process at this stage, after going through an exploratory data analysis phase, which was the second one, we were able to identify which attributes we're going to work with. Right, so if you notice, we've narrowed down our choice to these attributes here. Right, if I go up here, you will notice that we've filtered out, we've decided to get rid of attributes such as, Jesus, come on, attributes such as student name. We don't need the student name. Perhaps only thing we need is just the student ID, because this will help us uniquely identify that particular student. And in fact, once you load this information into pandas, when you're working with it within pandas, you can use the raw IDs as identifiers. So it could just as well have gotten rid of the student itself, student ID. But it turns out that in certain instances, as you are working through such problems, you might want to do a verification where you look up a particular student, and the way you look up a student is by using a unique key. So in this case, it would be the student ID, right? This is why we are preserving student ID in this case. Okay. So we've narrowed down to these particular attributes. We've gotten rid of some of these, and you notice that for entries such as or datasets such as the student demographic dataset, we've gotten rid of date of birth, because we have this derived attribute that tells us information that we can glean from the date of birth. Right, so we have student age, we have gender, we have minor description, sponsor. Granted, in this case, there's a bit of duplication here. We could just as well have gotten rid of one of these, the minor description or the minor. Oh, we have already gotten rid of it, actually. What I mean is, if you look at this data, you have, for the initial survey, one of the things we ask these students is to specify the minor, right? So if you notice, for this particular student, there's maths, there's languages. If we scroll down this sample 3 records here and get to the stage where we have the attributes coming in from the student demographic dataset, SIS, you notice that we have this same information, mathematics, right? So ideally, one of these should go. It may interest you to know that would actually get rid of the stuff that was provided as part of the initial survey, because information coming in from SIS is more authentic, right? So again, if you notice maths, French, we come up here, maths, languages, right? So this is much more authentic because it's much more precise. The other one is reported, self-reported. This is self-reported. This is extracted from the student information system platform. Okay, so we've settled down on these attributes. The goal now is to create a new data frame that is just going to be composed of these attributes. Now you notice that previously we were working with 153 attributes, right? Once we explicitly focus on the attributes that we've selected as or the attributes that we want to incorporate into the overall analysis, you notice that we'll end up with 114, right? So from 153 rows, 153 columns to 114. So we've managed to get rid of 39 redundant variables, right? Or useless variables, essentially. Now you probably sit there and you're asking yourself why this is important. At some stage, we get to introduce concepts such as dimensionality reduction, right? And this is at some stage when you're working with complex data sets, you will be working with a vector that has thousands of attributes. So what you want, thousands of attributes, means that you end up consuming a lot of computing resources. You want to get to a stage where you are able to consume as less resources as you can possibly consume. Why? The efficiency of the model itself is increased. Efficiency, right? Not effectiveness, efficiency. So the rate at which you'll be able to execute these different components of the pipeline will be much, much faster than it would be if you actually work with significantly larger vectors. Okay, so again, we inspect this to just try and pick at the attributes that we've selected, and you notice that we have them here now. And then we now start our data transformation kind of process. In this case, we're just going to look at a few examples. But before we get to a few examples, you notice that for each of the selected attributes, right? For each of these selected attributes up here, we go through a systematic process of reminding ourselves what sort of data transformation technique we need to use to convert it into a form that the estimator will be able to understand. So we know that hometown is categorical, and so it will have to use one-hot encoding. This is text content. We either use term frequency, count vectorizer, or TF-IDF vectorizer, right? Same goes for the major program motivation. This is text. If you look at this part here, the motivations here, this is pure text, right? And the list goes on here. And you notice, I just want to draw attention to things like the dependent variables or potential dependent variables that we'd use. These are assessment scores. You notice that there are certain data attributes like the percentage, which is already in numeric form. So this is the value that we scale to a percentage. It's from 0 to 100. Because it's already in percentage form, we don't have to fidget around with it. The status, on the other hand, the status, the grade, and the GPA are all categorical values, right? This is a categorical value, categorical value, categorical value. So we will need to convert it into a form that the estimators will be able to understand, into a numeric form, essentially. So all the status variables would have to be converted from categorical to one-hot encoding, using one-hot encoding, numeric using one-hot encoding. Just come on. This is one-hot encoding. This is the same thing here. This is one-hot encoding as well. All right, and of course, I mean, if we were working with the same data set, but a problem that was more focused on test scores and quiz scores, would essentially need to transform all these different things here, right? These dependent variables, because these would be dependent variables here. But for simplicity's sake, we're just going to work with the details associated with the final exam. And I think we've mentioned this already. So as an example here, we start with just basic label encoding here, right? So in certain instances, you might find yourself wanting to just essentially convert labels into numbers, right? What you can do for you to do that is you can take advantage of scikit-learn's label encoder object, right? So to work through this example, we first of all start by creating a data frame, right? After we create the data frame, we examine the exam grade, because we're working with an exam grade, here. We examine the exam grade to get a sense of the unique labels associated with this column or this attribute. So we see it's A+, supposed to be A+ up to D+, but it appears for this particular data set, no one got an A+, so we just have A to D+, A to D rather. Okay, or D to A, whatever you want to use. We create another data frame here just so we can use it for this particular part of the illustration. And then the first thing you have to do for you to use a label encoder is you instantiate a new instance of the label encoder class. Now you gain access to the label encoder class by putting this as part of your import statements, right? So you actually import this is label, not ordinary encoder, this is label encoder. You import the label encoder class from sklearn.preprocessing. Once you import it, you can then fit and transform. So fitting and transform is essentially just scikit-learn's way of saying you want to associate this particular encoder to this data frame, right? So once you fit and transform, you notice that you come up with numeric values that are associated with these particular labels. Right now, this label, the encoding of the label is usually useful when you're working with the target variable. So if you you have identified independent variables and you're trying to predict a particular target variable, that particular target variable you could sometimes want to represent it using these sort of numeric values, essentially, right? You also notice very soon, you get an appreciation very soon that you actually can take advantage of the label encoder, assuming that the order assuming that the order of these labels assuming that this is already ordered, you can actually use the label encoder to associate numbers to these things here, right? So you notice that the numbers that we have here would be I wonder if we can, the numbers that we have here correspond to these different categories. And I do believe once you fit and transform it, you should be able to, okay, so what I'm going to do is I'm just going to come up here and say, try and see if we can get the classes, right? So you notice that the classes associated with this label encoder, these A all the way up to D+, right? Hopefully that makes sense. Let's see if get parameters. Nope. Just try and see here. So incidentally, what I was wanting to do here is to try and see if we could identify the different classes here. So this is 1, 2, 3, 4. So meaning that the first observation has a C associated with the final exam. So the grade was a C. If I go up here and we check the first record, which is this entry here, the exam should be a C here, right? It's a C+. I'm wondering why there's something wrong here. I'm not really sure if this is preserved though. I'd have to confirm. 1, 2, 3, 4. Oh, sorry. Yeah, this is actually preserved. This is 0. If you notice, we have a 0. So A is 0, 1, 2, 3, 4. So what we're saying is that the first record, if you remember the sample we're looking at there, we just rendered out 3 records. So we're saying the 3 records for the exam score, we should have a 0, 1, 2, 3, 4, a C+. Oh, wow. A C+, an A, and a B. C+, A, and a B. C+, A, and a B, right? So that's for the label encode. All right, so hopefully that kind of makes sense. I think it does, to me at least anyway. So again, you always want to verify what you've encoded. For this particular example, we're just trying to showcase here that once we use label encoder on the exam grade, this is the sort of result that we have. So C+ is associated with a 4, and A is 0, B is a 1, 1, C+ is a 4. For ordinal attributes, it's pretty trivial thing to do here really is the only requirement for ordinal attributes is, as earlier mentioned, you want to make sure that the numbers you're associating with the labels are ordered or are representative of the weighting associated with the labels. So in this particular example, we're going to work with the experience with computers attribute, and we have these different unique values where A student could either have no experience using computers, less than 1 year experience, 1 to 2 years experience, and more than 5 years experience. Now, for simplicity's sake, you will notice very soon here, so we create a data frame here. You'll notice very soon that we will associate incremental natural numbers, essentially signaling the fact that the difference in between these different experiences is the same, right? What would be implicitly saying, or the message would be implicitly sending to the estimator, right, would be that the difference between someone with no experience and someone with 1 year experience is the same as someone with 1 to 2 years experience and more than 5 years experience, which is not true really. But for simplicity's sake, this works just fine. So again, you create a data frame here that selects entries where the experience working with computers is not now, for the purposes of this example. And then we just select these particular columns here for our analysis. We inspect our newly constructed data frame. You notice we just have student ID, experience with computers, and the examination status. Remember, again, what we're trying to showcase here is how we get to convert these to numeric values. Numeric values that signal, that implicitly tell us the relative weight associated with these different labels. Again, we just, for good measure, we just, we inspect or we extract the unique, we print out the unique entries associated with these different labels. And you notice that we also have missing data here, which is fine. In an ideal case, we probably should have filtered out missing data. So the first approach is this. I use this a lot. I just take advantage of some of the features associated with Python where I will create a dictionary mapping, right, and associate the weightings to those labels. So you notice here I'm saying no experience is going to be associated with 1, less than 1 year is 2, 1 to 2 years is 3, more than 5 years is 4, missing is 5. I could just as well have said, oh, if someone has no experience, then the weighting is 0. If they have less than 1 year experience, the weighting is 3. If they have less than 2 years worth of experience, this is 2, this is 3, and this is 4, right? And then I'll create this dictionary. Now I'm creating this dictionary because I want to just showcase what I want to do here. I want to add an additional column to this data frame that is going to have these particular numbers. So for all occurrences where an observation is associated with no experience, I'll have 0 associated with this newly created data frame. Essentially what we're doing here is we're saying selected, not 3D performance. This is called Arduino example 1. Jesus, Arduino example 1. So what we're saying here is that experience with computers. What we're saying here is that if we take a sneak preview of this thing here, with one record alone, this is what we have, right? So what we want is a sort of situation where we replace all occurrences of this label with the corresponding numeric entries here. And I'm pointing at the screen with my thumb, but you can't see that. Oops, sorry. All right, so we do that. What we want is this kind of situation here. You notice that I've now replaced all occurrences of, observe, all occurrences of these labels are mapped onto these numeric values, right? Confirmed that, avoiding a lot of entries here. So we confirm that this works. Once we confirm that this works, we are adding a new column called experience with computers encoded onto this existing data frame. In an ideal case, you probably would want to replace this. So you overwrite this with a numeric, because essentially, once you get to a stage where you encode a label to its corresponding numeric value, you don't need the label anymore. It becomes pointless for you to include it. So you delete it, you drop it. But for the purposes of what we're doing here, this walkthrough, we won't drop it. Because we want to see the corresponding numbers associated with the labels, right? No experience is 0, 1 to 2 is 2, less than 1 experience is 1, no experience is 0, right? So you'd have then applied, you'd have encoded these ordinal labels, right? Another way of encoding ordinal attributes is by using the ordinal encoder class from within scikit-learn.preprocessing. And again, to showcase this, we create a completely new data frame that we're going to work with for this particular example. First thing you do is you create an instance of the ordinal encoder class. And again, for all these different classes, by the way, I'm making use of, you always want to get to a stage where you can look up the help files to gain a sense of what sort of parameters you can feed it, right? Turns out that this is extremely helpful, right? So you want to develop the habit of reading through these. But for now, the default is fine for the purposes of this particular example. So the first step is you create an instance of the ordinal class. Once you create an instance of the ordinal class, and I can't check the categories. I'm wondering why I check the categories here. Okay, so in certain instances, you might want to specify the actual explicit categories associated, and I think I showcased this just now, categories. You might want to specify the order of the categories, right, that you want to encode, right? So in this case, you would say, oh goodness. I think maybe we might have to showcase this just to. So we have experience with computers, right? Which is this. We could get the unique entries here so that we use these as categories. One of the things you can do is you can feed this particular encoder, the ordinal encoder, with categories, right? And we don't want to pollute that. I'll come here and then just ASK then the preprocessing import ordinal uppercase O. Come on. All right, so what we're saying is we're going to say label var ordinal encoder is equal to new ordinal encoder, no new here. What we're saying is we can, if we just check the categories associated with this default class without any parameters here, Jesus, this is what we get. But if we create, yeah, Jesus Christ. But if we create, I do apologize for that. If we create this with so we create a class without any parameters. This is what we get, right? Auto categories. But if we create it in such a way that we explicitly specify that there's some order associated with the data, assuming this is ordered, we use the category parameter like so. Categories is equal to, give it a list like so, so that when you run the categories, it will show you the order of the categories. But that's besides the point. Anyway, I guess the key takeaway point here is you always want to look up these different classes and functions that you're using so that you understand how they work, right? Help is usually very helpful. Help is usually very helpful, right? Okay, so once you create an instance of this class, you then fit and transform, right? You tell it exactly what sort of ordinal values you want to associate with this ordinal encoder instance. In this case, we're saying we want to run this on the experience with computers. Experience with computers column, right? Okay. And then again, for good measure, we just take a peek of what we've just encoded, and you notice that again, similar to what we had before, we have numbers associated to this. Now, this is, I guess, a classic example of why you might want to use, you want to explicitly specify the order, because you clearly notice here that 1 to 2 is given 0, 4 is given no experience, right? Because it's using this order here, 0, 1, 2, 3, 4, right? So you probably want to play around with the ordinal encoder using the categories parameter and see if you can play around or fidget around with the order of the numbers, of the labels themselves. But I personally prefer to use the Pythonic way, right? Just using good old dictionary and then provide a mapping. It doesn't matter, you can use whatever works for you. And really, as you are working through a number of these problems, you're practicing with scikit-learn and Python in particular, you notice that you find different ways, and in fact, in certain instances, more effective and efficient ways of writing code, right? So you don't have to mimic what I showcase in here. Okay, so next up is nominal attributes. Remember, we mentioned that with nominal attributes, the way that we encode nominal attributes is by taking advantage of so-called one-hot encoding, right? So want to get to a stage where we transpose the labels and then binarize the values associated with the transposed data frame or data structure, right? So again, we just spit out the columns that we want to encode using one-hot encoding, right? These are all nominal attributes here clearly, right? There's no order associated with pass or fail. Well, I mean, that's debatable. I guess you could argue that pass is greater than fail. I don't know. But if you look at the manual description anyway, there's no order associated with English, civic education, or maths, at least within the context of what we're doing, right? So using pandas, there's two ways of converting from this sort of format to a one-hot encoded equivalent of this. There's a pandas way, and then there's a scikit-learn way, right? So within scikit-learn, you have access to from sklearn.preprocessing, you have access to one-hot encoding class. Jesus. You have access to this one-hot encoder class, right? So you can encode using scikit-learn, or you can use pandas. Now again, I prefer pandas myself, but if you want, you can use scikit-learn. I'm sure there are other ways of encoding data, right, from this sort of form into a one encoded format. Remember that the one encoded format we're talking about is this sort of format here, right? This transport format. I'm guessing you could probably come up with your own way if you want to, but it would be pointless. What I thought we'll do is the scikit-learn example, scikit-learn approach will be an exercise for you guys, but I'll show us the pandas way of doing this. Pretty trivial. Pandas has a get dummies. It has a get dummies function, right? So you access it by using pandas.getDummies function. You apply the pandas.getDummies function to in this case it would be to the data, the column that has the labels that you want to one-hot encode. So in this case, we want to one-hot encode pass and fail. And you notice that we're just running pd.getDummies to get this transposed form here. Observe, right? If we, before we do this, if we say we want to take a look at take a look at the exam status column, you notice that you have pass, pass, and fail, hopefully, right? Passes, and I'm sorry for the noise, I don't know what's going on outside, but we have pass and fail. But when we apply the pd.getDummies, we get this one hot encoded format, right? And again, this format is, by looking at this format, you can tell that it tells you that this is a pass. If we got 10, it's a pass because you have a 1 associated with it, and we can tell that this was a fail, right? So quite easy, really, again, to showcase on attributes, more than 2 attributes, or more than 2 values rather. This time around, using the minor description, this is a sort of format that you get. Again, if we were to view this in its normal form, this is what we have, right? So we have these labels, and then when we use the pd.getDummies function, we get the equivalent transposed format, right? And by looking at this, you can easily tell that this particular observation is associated with maths. This observation with ID 2 is associated with French. This observation is associated with religious studies. This is what you want to get at. All right. Again, to showcase how exactly this works, we're just going to merge the actual labels and the one hot encoded equivalent so that we gain a sense of how this is done. So you can see here, this observation is English, and then when you one hot encode this, you have this sort of thing here. And again, by just looking at the one hot encoded values, you can tell that wherever you have a 1 is a flag indicating which label is associated with that observation. English, missing data, mathematics, English, civic education. Great. You probably have a lot of fun looking up how to use the one hot encoder class, right? To encode. Okay. All right. So just to mention here again, we're just looking at categorical data here for now, right? Nominal and these are nominal attributes you're looking at. Previously looked at ordinal attributes, but just to mention that there are other techniques out there. Like you can take advantage of so-called dict vectorizer. Is it dict binarizer? Dict. Ooh, is it? If I have this here, I think there should be a dictionary binarizer as well. Let me just sklen dict binarizer. I hope it's there. I don't know if I was dreaming about this label. Oh yeah, vectorizer. Wasn't, I thought there was a dictionary binarizer or something. Looks like there isn't, which is a bit weird. I thought there was. Anyway, there are a couple of other techniques that you probably come across as you're researching, right? I'm just showcasing an example here of multiple label binarizer. I guess in instances where you might want, you're solving a problem that involves predicting multiple results associated to an observation, and I guess this comes up a lot. For instance, when you're searching for literature, if you write something, you tag it with subject keywords. It could be computer science, data mining, computer science, software engineering. So all these different labels will be associated with that entry, and so you could take advantage of the multi-label binarizer, right? So if you look at this particular observation, what we're saying is that there are 2 labels associated with it, which is this and that, right? Yeah, you probably want to look up dict vectorizer as well. And I'm sure there's a lot more stuff that you probably find out there, right? But the bottom line here is we're just trying to showcase examples of encoding categorical data, right? All right, I'm just going to pause for a little while and then we'll continue with walkthrough of text encoding by just focusing on TF-IDF and